start out discussing correlation and association between continuous variables. And just to start out generally, we have the question, what is an association? And two variables can be said to have an association if, as the values of one variable change, the values of the other one also change in a systematic manner. So for instance, in general, as a person's height increases, so does their weight. In general, as age increases among adults, so does their use of healthcare services. Usually we call one variable the independent variable and the other variable the dependent variable. And when it comes to associations, we're interested in both the strength and the direction of the association between the two variables. And so in order to get our data for studying associations, we obtain a random representative sample of individuals from our population of interest, and then on each individual we want to measure both variables of interest. And typically we're going to call the independent variable variable X, and that's going to be shown along the horizontal axis of a graph, and the dependent variable we're going to call variable Y, and that's typically shown along the vertical y-axis of a graph. And so in the data set, each variable would be entered as a column of data. So you'd have your individual identifier, and then you would have variable X as one column, variable Y as another column. And so each case is a row for the individual that contains that individual's measurements for X and Y. And so when we think about associations, we want to ask the question about whether associations represent a true causal relationship or are just merely coincidences. So for instance, this graphic is showing you that there appears to be a very clear relationship between babies in millions and storks in thousands in this hypothetical population over time. And so, if we were just to look at this data, we might think, maybe there's some kind of relationship between the number of storks and the number of babies. However, that doesn't seem very plausible. And so we want to think about one of the most important things I can emphasize that you've probably heard before is that correlation does not mean causation. And so just because you see an association in the data does not mean that there's a cause-effect relationship. And we've discussed this earlier in the course, but there are some basic criteria that we have for inferring cause-effect relationships from associations. And so, for one thing, we would want the association to be documented by multiple studies at multiple sites by multiple investigators using different methods. And so this would reduce the likelihood that an association is just some kind of artifact of a particular study design or methodology or just a coincidence. It's also important for the association to continue to be present when the effects of other plausible hidden variables and alternative explanations are eliminated. And so we would want to make sure that we're controlling for other variables and considering other alternative explanations. And so oftentimes we do this by very closely controlling the experiment, and that's why randomized, double-blind, randomized controlled trials are considered the gold standard in research, because this is what they in fact do. Secondly, if we're just talking about observational data, we want to think through the statistical methods that we're using when analyzing the data to control for these other hidden variables and to try to rule out alternative plausible explanations. And so, one way of saying we've identified a cause and effect is that we also want to be certain to have a plausible mechanism, a plausible cause-effect mechanism that explains the covariation of two variables. So part of this is just logic, right? There's no logical, plausible mechanism, cause-effect mechanism going from any kind of association between storks and babies. However, if we would think about some other instances, such as having health insurance, for instance, we know that that makes purchasing healthcare more affordable. So we would expect having health insurance to be positively associated with utilization of health services. Secondly, we also know that managed care, one of the goals is to control or reduce inpatient hospital utilization. So we would expect that in markets that have a higher managed care market share, we would expect there to be a negative association with inpatient hospital utilization. So part of this is being able to use logic and tell a good story. Okay, so let's define some key terms now. An association, which here we're focusing on correlation, is a statistical pattern of covariation among two variables. So there's just covariation. A relationship we would define as a cause-effect linkage between two variables. And so as I mentioned earlier, a correlation is not equal to causation. And so, we can study correlations using statistical analyses and discover them, but that doesn't mean we have a cause-effect relationship. And causation is really what we want to get at in order to make valid predictions across time and space. So let's take an example here of a strong correlation and relationship. This is the relationship between contraception use in a population and infant mortality. So contraception use is on the horizontal x-axis, infant mortality on the vertical y-axis, and as you can see, it appears that as a greater percentage of people in the population use contraception, we see infant mortality also at a lower rate per 1,000. And so the question is, well, does contraception in and of itself reduce infant mortality? It seems kind of odd that would happen, right? And so you want to start thinking about, when you see associations, about other kind of plausible alternative explanations for the association. For instance, we know in societies that are economically developed, we tend to see better healthcare systems, better educational systems, and more opportunities for women. So with a better healthcare system, we would expect to see reduced infant mortality. Other studies have shown that when we see better educational system and more opportunities for women, there tends to be increased availability and demand for contraception, which is going to lead to increased use of contraception. So you can see there are some other plausible alternative explanations for the association that we just saw on the prior slide. So now let's talk about statistical analysis for association. So the main kind of analysis is correlation analysis. And so correlation analysis provides us with two pieces of information. First is the direction of the association. Is the association positive or negative? Second is the magnitude of the association. This lets us determine if the association is strong or weak. And so correlation analysis only works with two variables at a time. For example, we can only consider whether the number of hospital beds is related to length of stay, or whether managed care market share is related to length of stay. But we couldn't consider both of those scenarios together, because then that would mean involving three variables. Regression analysis, on the other hand, which we're going to discuss in the next module, we can also determine the direction and strength of an association like correlation. However, we can consider multiple variables simultaneously, so more than just two variables. For example, our managed care market share and the number of hospital beds related to length of stay. So length of stay would be our dependent variable, managed care market share and number of hospital beds could both be our independent variables, and we could add more variables as we'll discuss later. And in addition, regression analysis provides us with additional statistical techniques that allow us to get at cause-effect relationships. Okay, so now back to correlation. And so the first place to start when thinking about correlation is with graphs. And so here you can see on the scatter plot of the relationship between two variables on the y and x axis, and this scatter plot shows a clear positive association with a straight line going up from the origin there in the graph. This would be, and each point is right as a coordinate for an individual showing their x and y values. And so here there's this clear, strong, linear positive association. As x increases, the value of y also increases. And this is quite strong, you can see the values are clustered along this line in a pretty tight pattern. Another example would be a negative association. So in this example, as x increases, going from left to right, the value of y tends to decrease. This association isn't quite as strong as the association we saw on the previous slide, so the patterns for each individual observation are a little more diffuse, but there's a clear downward slope to this cluster of observations here. So this is a weaker association than the prior slide, but definitely a clear negative association. If you want to think about what no association would look like, here's a good example. It would just be a bunch of dots all over the x and y coordinate of the graph, and there's no clear linear pattern here in the data. So as x increases, there's no kind of systematic change in the value of y. And so the particular statistic that's used with correlation analysis is called the correlation coefficient. And this is a sample statistic that quantifies both the direction and strength of an association. And so the sign of the coefficient can either be positive or negative. And this indicates if the association is positive or negative, like we saw in those graphs. The value of the correlation coefficient ranges between -1 and +1 and indicates if the association is strong or weak. So any values that are close to 0, whether positive or negative, that means a weak association. Any values that are close to -1 at one extreme end or +1 at the other extreme end, those are considered very strong associations. And here's the formula for the correlation coefficient. It's often symbolized by the lowercase letter r, also called the Pearson correlation coefficient. You can see in the numerator there, this should look familiar, where for each individual observation x, we're subtracting the mean value. We're also doing the same for each individual observation y. We multiply those together for each observation, and then we're summing them, and that goes into the numerator of this equation. And then in the denominator, we have n-1, which is the sample size -1, and then we have the two standard deviations, both for x, the standard deviation of x, and the standard deviation of y, and we're multiplying that together, and that gives us our formula for the correlation coefficient. Excuse me. And so the formula on the top there also comes out to the same as the formula on the bottom, where you're taking the sum of squares for the variable x and the variable y in the denominator and multiplying them together and taking the square root. And so, what are some assumptions when we use the correlation coefficient? Well, for one thing, this method assumes that both variables are normally distributed and that a linear association exists between the two variables. And as I mentioned, the correlation coefficient ranges between -1 and +1. And so you can see in the equation on the bottom here, the denominator of the equation for r is always positive, right? Because we're taking this, multiplying the sum of squares, and sum of squares are always positive. However, the numerator is what can be positive or negative, and so that gives us a positive or negative value for r. And so in this graphic, what I'm showing here is the sum of the cross products that are in that numerator, right? You have, you're subtracting the mean from each individual observation of x, and ditto for y, multiplying them together. And so when you take these cross products, the sum of them can either sum up to be positive or negative. If it's negative, you're going to see values that tend to fall into the upper left and lower right hand side of this coordinate system in the graphic if we're displaying y and x. And so the straight lines here are the mean of y. The middle is the mean of x and the mean of y. If we tend to see positive values on these cross products, that could be because we're seeing either positive x, positive y, or negative x, negative y, and which would, when you multiply it out, give a positive. And so then you would see values on the lower left and upper right hand side of the quadrant, and that's how we would get a line that slopes up in a linear fashion from the origin. And so, what we're taking is we're summing up all these cross products for everyone, right? And so if you think about it in a positive association, most of the cross products are going to be mainly positives. You're probably going to have a few negative values, and the sum is going to be a large positive value, and R is going to end up, the correlation coefficient is going to end up being close to +1, and then you're going to see this line sloping up from the origin of the graph. On the other hand, if we're thinking about a negative association, the cross products and the numerator are going to mainly be negative, but you're also going to see a good deal of some positive values in the other two quadrants, but the majority are going to be in the upper left and bottom right quadrant. So you see this line, if you put it through the middle, that would slope downward. The sum is going to end up being so again, this is for the graphic that we saw previously. The sum in that case would end up being a modest negative value, and R is going to be, I think it was 0.6 something that we saw, so between 0 and -1. If there's no relationship, right, the cross products in the numerator of our equation for R are going to be pretty equally distributed between positive and negative. And so when we add all these positive and negative numbers up that are pretty equally distributed, the sum is going to be very small, and the value of R, our correlation coefficient, is going to be close to 0, which means no relationship. So let's look at two examples here. These are the graphical examples we saw in prior slides. On the right-hand side, you're looking at a correlation coefficient of 0.98, very strong positive linear relationship, and you can see, sure enough, you draw a straight line through it, and the points are tightly clustered along that line moving up from the origin. On the left-hand side, we're seeing a weaker but still very discernible negative relationship with a correlation coefficient of -0.69, and you can see that the clusters are a little more diffuse, but definitely still along that negatively downward sloping line. And so those are two good examples of the correlation coefficient. If you want to think about two other examples of the correlation coefficient of no relationship, you could either have on the right-hand side this very diffuse pattern of the x and y coordinates and write our R as 0.04, so that basically no relationship. Or you could have them tightly clustered along a line, but it's a horizontal line, so there's still no relationship, discernible relationship between x and y. It's that horizontal line is basically the equivalent of random chance. Okay, so just because there's not a linear relationship in data doesn't mean that there's not a relationship, right? And so this graphic that you're looking at, clearly there appears to be a relationship between x and y, right? As x increases, y decreases up to a certain point, which looks like it's about the mean of x, and then after that point, that appears to be an inflection point, the values of y increase. So this is an example of a nonlinear relationship, and the type of relationship that Pearson's R, our correlation coefficient, is unable to detect. And so this is why we can only use this correlation coefficient to describe linear relationships. Okay, so it turns out that R, the correlation coefficient, has a sampling distribution. And remember, I said it ranges from -1 to +1. The mean is around 0. And so, as you can see, this sampling distribution appears to be have a fairly normal shape. And so, the good news about that is that this distribution actually corresponds to a t-distribution. And so, we can conduct statistical tests of null hypotheses for the correlation coefficient R. And so if there's no association at all, we expect R to be 0. So this is also the mean or the expected value of R, which you can see from the way the data is distributed around 0 there. And the standard deviation is given by the equation there. So you take 1 minus r squared divided by n minus 2, and then you take the square root of that. And as I mentioned, the shape of this follows a t-distribution, and the degrees of freedom are equal to n, the sample size, minus 2. And so what this means is we can do hypothesis testing, right? And so our null hypothesis for the correlation coefficient r, we remember when you think about the null hypothesis, you want to think about the population parameter. And so the letter that's used for the population parameter for R is actually this Greek letter rho that looks like a P. And so we hypothesize, our null hypothesis is that the population parameter is 0. So our null hypothesis is that there's no relationship between these two variables. So set up the null, that's rho equals to 0. Our alternate hypothesis could be that rho is not equal to 0, that there is a relationship between the two variables, or that it's greater than or equal or less than or equal to 0, right? We could specify a direction in that relationship. So our next step would be, as always, we would want to identify our desired alpha value, typically alpha 0.05. Our degrees of freedom, that's always n minus 2. And then, just like you've done previously, you want to use the t-test and look up in the t-table and find the critical value of t for rejecting the null hypothesis. And so use the same process there as you have, we went over in prior lectures for one- and two-tailed testing with the t-distribution. However, when you actually compute the t-statistic for the correlation coefficient r, that is a little different. So you can see the statistic there. In the numerator, we have r multiplied by the square root of n minus 2. And then in the denominator, we have the square root of 1 minus r squared. So we compute that t-statistic, and then we compare it to the critical value, and we either reject or fail to reject the null hypothesis. One last thing before I end here, I want to talk to you about the coefficient of determination. So this is simply r squared, which is the correlation coefficient squared. And what this is r squared is actually the proportion of total variation in the dependent variable y that we're interested in that is explained by the independent variable. And in general, only some of the variation in y is explained by x. And so all we do is, to get this, we take the square of the correlation coefficient. Note, however, that the correlation coefficient, because we're taking the square the coefficient of determination is only positive, right? The correlation coefficient ranges between -1 and +1, but when you take the square of that, it can only be positive. So it ranges between 0 and 1. For the coefficient of determination. Also, you should note that the same assumptions that apply to the correlation coefficient also apply to r squared. Okay, so I'm now going to walk you through a demonstration in Excel. So be sure to watch that. And you can basically, I want to show you how to do data analysis for correlations. It's very useful. Basically, you set up the variables in contiguous columns, as I mentioned earlier, and then all these pairwise correlations are then calculated. And there's actually a formula in Excel to do that, rather than you having to compute the mean differences and square them by hand yourself. Another really valuable thing to do, probably the most important thing to do first when you're looking at two variables in Excel, remember these are two continuous variables, is to just graph them quickly using a scatter plot. And so if x and y are in adjacent columns, you just highlight both and create a graph, and that will very quickly show you, based on the cluster of dots, whether there's a relationship.